Welcome to lecture 22. In the last lecture, we saw the Markov inequality and Chebyshev inequality. We'll start by recalling the same. So the Markov inequality applies to non-negative random variables with finite expectation. It tells you that the probability that x exceeds some alpha times mu, where mu is the expectation of x, is upper bounded by 1 by alpha. And Chebyshev needs an extra condition. It does not need the non-negativity, but it needs a finite variance. And unlike Markov, it's not a bound on x being greater than some value. It's about x deviating from its mean mu by more than alpha times the standard deviation is upper bounded by 1 by alpha square. So here the interesting fact is that if this decay is like 1 by linear, this is 1 by quadratic. So it is considered better than Markov, but again Markov is tight in its own sense because there could be random variables where the variance does not even exist. Okay. Now you can extend this idea quite a bit, okay, and finally we will reach what are known as a class of bounds called Chernoff bounds. Okay, even the Wikipedia article about Chernoff bounds lists a lot of them. So, but we will only, at least for most of this course, we will narrow it down to one particular version of the Chernoff bound, but you are encouraged to look at the Wikipedia page to see various different forms of the Chernoff bound. Okay, and the Wikipedia page also again, like this Markov inequality, also starts with a controversy as to who really discovered this Chernoff bound. Wikipedia at least says it's not due to Hermann Chernoff, but due to Hermann Rubin. Okay, but anyway, both these bounds are around old. These are later than this Markov and Chebyshev. This is more like 1950s, right? Where others were much older. Okay, so yeah, as I was saying, we can extend this idea of Chebyshev if you have a guarantee that larger moments will exist. For example, if the random variable x has expectation mu and a finite fourth moment, okay, and a finite fourth moment, I'm just denoting it as gamma to the power 4 so that like we denote the second moment as sigma squared, second central moment rather. So here I should, though I wrote finite fourth moment, I should have been, the more correct way to call this is the fourth central moment. But yeah, if the fourth moment is finite, if and only if the fourth central moment is finite. So yeah, under this case, a direct application, again, like we proved Chebyshev, which was by applying Markov to the random variable x minus mu the whole squared. Similarly, you can prove this bound written here by applying Markov to the random variable x minus mu to the whole power 4. Okay, because x minus mu the whole power 4 exceeding some constant times gamma power 4. So I'll take that constant to be alpha power 4 is 1 by alpha power 4, and then this event I can equivalently represent by taking the fourth root, which would be like modulus of x minus mu greater than or equal to alpha gamma. This I can do for sixth moment, eighth moment, or in general any even moment. So if a random variable x has expectation mu and a finite 2kth central moment, again where I denoted by, this is only a notation, I could have just denoted it by delta, but in this case then here instead of delta you will get a delta to the power 1 by 2k. So in order to avoid that, I denoted the moment by delta to the power 2k. If that exists and is finite, then by the same trick I can get a 1 by alpha to the power 2k dk. But again, this is, remember here it was sigma here, then it's alpha times sigma here, it's alpha times gamma here, alpha times delta here. They may be different, okay? So it's not a direct comparison, but most of the time as long as these guys are constant, that does not matter. It's the rate at which the probability decays that's going to matter, okay? Now we can actually extend this even one step further, and that is how most of these Chernoff family of bounds follow. Okay, so suppose this random variable x, again with finite expectation mu, that does not change, but instead of assuming some finite 2kth moment, let's say we assume that some finite exponential moment, something like expectation of e raised to x minus mu rather than x minus mu to the power some even number. We have, let's say, expectation of e raised to x minus mu xs. Okay, but now Look at why did we, by the way, restrict to even sized moments? That is, because we have to talk about, use this Markov, and Markov was guaranteed, Markov in its assumption needed a non-negativity. Okay, so x minus mu to the power 3, for example, may not be a non-negative random variable. Now, e raised to x minus mu for any real number, e to the power that real number is non-negative, so this will work. Okay, e raised to x minus mu is indeed a non-negative random variable, and hence you can apply Markov. So the probability that e raised to x minus mu exceeds some constant times its expectation. But what is its expectation? Its expectation I am just denoting by e raised to zeta. Okay, I mean I could have just denoted it by a constant zeta, but then later in the bound it would become a log of that constant I denote here. Okay, so just for notational convenience I am calling this e to the power zeta, and this constant again I am calling e to the power alpha instead of just calling it alpha. Then what do I get? I get, taking natural logarithm on both sides of the inequality, I get, okay, do I really get modulus of x minus mu? I don't think so. Okay, so yeah, probably I should have taken e raised to modulus x minus mu. Yeah, but then that's not called the central moment, but yeah, but this is also okay. Okay, so you will get a probability that x exceeds mu plus this zeta plus alpha to be upper bounded by 1 by e to the power alpha. Okay, so let me not go and kind of correct this here, because again, as the next remark says, no one wants to compute or use these higher moments, exponential moments in general. Okay, most of the time you want all these statistics in terms of first moment and the mean and the standard deviation, mean and the variance. And there are certain special cases where this can be reduced to that with some effort. I mean, there is some amount of calculation involved in proving any of the Chernoff bound, and we will see only one example, the most basic example. Okay, so yeah, in fact we will only see a special case. Okay, what is a special case that we will see? We will assume that our random variable x is a sum of independent Bernoulli P random variables. Okay, so this is in fact a sum of an i.i.d sequence. The independence is essential in the assumption, and everything is Bernoulli P, which means actually I should say everything is 0, 1 Bernoulli P, because some people call Bernoullis to be -1 + 1. But we are going to assume that they are 0, 1 Bernoulli P. What does that mean? That means each xi takes a value 1 with probability p and 0 with probability 1 minus p. This is the most common scenario that we encounter in combinatorics, right? Because these xi's are going to be indicator random variables of some very atomic events, and hence it's most of the time either 0 or 1, with 1 being the probability that this indicator event is happening. Okay, so under this context, we want to estimate the probability that this x is more than 1 plus epsilon times mu. Okay, now this you can compare it with bounds that we have already seen. This is like probability of, okay, again I cannot write an absolute value. I'll work the lower and the upper tail separately. So this is like, this 1 plus mu, I take it here, right? Then yeah, it looks almost like a Chebyshev bound, but without the but with two differences. One is that you don't have a magnitude here, so you'll have to have one bound for x minus mu and the another bound for minus of x minus mu. Yeah, and also this is not epsilon sigma, this is epsilon mu. Okay, so yeah, those differences are there, but in some kind of a structure, this is also a deviation bound. Okay, this is also a tail bound. That's all that I wanted to remark. Okay, now let us start dirtying our hands and see what kind of a bound can we achieve here. Okay, I'll prove the bound and then state the Chernoff bound as a result. So, but the proof technique should be clear. We will you are going to use apply Markov inequality to e power x, but rather than applying it to e power x, it turns out that you can put in a constant lambda there, which is positive. So for every lambda greater than 0, this e power lambda x is a monotonically increasing function of x, right? So since your e power lambda x is a monotonically increasing function, x greater than something is equivalent to the same event. You can write it as e to the power lambda x greater than or equal to e to the power the right hand side. Okay, e to the power LHS greater than or equal to e to the power RHS, and this is true for every positive lambda. Negative lambdas it won't work, right? Then the curve may go not be monotonically increasing. But what is lambda here? Lambda is a constant that we are currently putting in. Later, towards the end of the derivation, we will do some calculus and optimize it to get the best possible bound. Okay, so yeah, so now I want to apply the Markov inequality, but for that I should write this as some constant times the expectation of e to the power lambda x. In this case, there is no magic there. I multiply and divide by e to the expectation of e to the power lambda x. So this RHS by e to the power lambda x turns out to be the constant, and now this is a positive random variable, and the Markov inequality gives you that this is 1 by this constant, the reciprocal of this constant, which is this guy. Okay, so this equation we will denote by 1. Okay, so the probability that we are going to analyze is upper bounded by this quantity here, expectation of lambda x divided by this. Okay, so as you can imagine, most of our computation will be on the numerator. The denominator is already in a nice form. Okay, so let's only analyze the numerator of this equation 1, which is e to the power expectation of e to the power lambda x. Now x is a sum of indicator random variables. Now e to the sum decomposes as a product of e to the corresponding powers, right? So the sum in the exponent comes down as a product of these guys, and this is where we are going to use the mutual independence, right? Remember, the xi's were not just identical, they were also independent. Okay, and so here from this point onwards, this analysis only works for this special case where your x is a sum of independent random variables. Actually, identical is not the most important condition. The identical helps in the next step, where this product you can equate it to just a power. Okay, that's where the role of the xi's being identically distributed comes in. Okay, so as of now, this expectation going inside a product is true only because of mutual independence. Expectation will go inside a sum without any precondition, but expectation will commute with a product only if there is a independence. And now, because of the identical nature of xi's, e to the power lambda x1 expectation or the expectation of e to the power lambda x2 all are same. So this whole product business becomes a power of n. Okay, so which means in order to analyze the numerator, I only need to analyze e raised to lambda x1. x1 is such a simple random variable, right? It's an indicator random variable. And then I can take the nth power. What is e raised to lambda x1? By definition of expectation, it is p times e to the power lambda x1 and 1 minus p times e to the power lambda 0. Okay, x1 can take either 0 or 1 with probability 1 minus p and p respectively. So this is the expectation. E to the power 0 is 1, so that gives a 1 minus p, and you have a p e to the power lambda. I group it in this way, 1 plus p times e raised to lambda minus 1, and our favorite usual bound 1 plus x. Here x is this p times e power lambda minus 1. 1 plus x, I'll upper bound by e power x, which will give me this. Okay, you can work with this bound, but then it gets ugly as you go along. Okay, you want everything to be in this exponential form, so that when you now put in this n here, it's just going to be some np e to the power np e raised to lambda minus 1. Okay, so this is equation 3. If I substitute in 2, what I'll get is the numerator is upper bounded by e raised to np e to the power lambda minus 1, and I substitute in back in 1, which essentially means bring back the denominator also. So you get this, yeah, e raised to np e to the power lambda minus 1 by the original denominator. Okay, now it's a very nice form, e to the power some x by e to the power y, which is e to the power x minus y. This much is fine. This is the point where you are ready to find the best lambda by doing some calculus here. Okay, so mu is a common factor here. You can actually ignore the mu, but okay, I have written the mu anyway. So this is the we express this, consider this as a function of lambda and take its derivative with respect to lambda. you can see that this, okay, mu I should have cancelled out in the beginning, but it's okay. Yeah, e raised to mu e raised to lambda will give you mu e raised to lambda. This is -1 is a minus mu is a constant dice where you differentiate, and here again your lambda is your variable of differentiation. You are left with a -1 plus epsilon mu, and we set this to be equal to 0 to find the best lambda. So mu goes away. The solution is e raised to lambda is equal to 1 plus mu, or equivalently lambda is equal to ln 1 plus delta. Okay. So now we go and substitute in 4 these values of lambda. Okay. So yeah, wherever when here there is a lambda where I can use this formula, here there is an e raised to lambda where I can use this formula. So yeah, putting them together, this is the same LHS, e raised to mu. Yeah, this e power lambda becomes 1 plus epsilon minus 1, so which is just an epsilon. And this is minus lambda becomes minus ln 1 plus epsilon. Then this 1 plus epsilon mu remains. Okay, so this is just a rearrangement of these guys. This minus mu I pull out of this, that is 1 plus epsilon ln 1 plus epsilon. There would be a minus epsilon here. Okay, now in some sense this is a final bound, but we will try to convert this into a more memorable form. Okay, by actually losing something. So this is an expression that only involves epsilon. Okay, and in fact it's actually a good epsilon. This is only like a linear plus logarithmic, right? So it's almost linear in epsilon, which when we are very hard pressed and we want a really tight bound, you should probably just retain this. But we will we need a simple bound that is easier to remember, and I'll break the surprise, and finally the easier bound will be something like epsilon squared by 3. Okay, it's quite bad. Instead of linear plus logarithmic, it's kind of changing n log n to n squared, right? Yeah, but yeah, let's anyway do it, because that's the way Chernoff bound is most often written. Okay, so what we need is, let me call this function f of epsilon, this 1 plus epsilon ln 1 plus epsilon minus epsilon, and then try to find what kind of a bound for. So this is an upper bound. So now this is an exponent but with a negative sign. So I am actually looking for a good lower bound for f of epsilon. Okay, so I want a lower bound. Yeah, I need a simple lower bound for f of epsilon. Now let's see what is this one. Let's expand this using our famous series expansion for ln 1 plus x. Okay, so ln 1 plus x is this guy here, x minus x squared by 2, etc. X times ln 1 plus x is just everything I'm getting shifted. This is x times this is x times this, and so on. Add them, you get 1 plus x ln x to be x, and there is an x squared by 2. Now you do the subtraction, you will get an x cubed by 6, you will get an x power 4 by 12, and so on, right? But then the point is that we want a lower bound for this. In fact, we want a lower bound for this minus x, right? But we will now use the fact that our epsilons are going to be small numbers. In fact, we will assume that our epsilon is within the range 0 to 1. So I can assume that this x is going to be epsilon later. So I'll assume x is less than 1. And then if you analyze this guy is positive, okay? Because this is some x power 4 by 12. This is x power 5 by 20. So the denominator is already larger. So this is again smaller. But in addition, x is also at most 1. So this having one extra power of x is to your advantage. It only makes this smaller. It does not make it bigger. So now if you pair up all the remaining infinitely many terms, all of them are positive, and hence this much turns out to be a lower bound. Okay, and here also I can kind of lower bound this x squared by 2 minus x cubed by 6 with x squared by 3, right? There again it is the same idea. Your minus x cube is at most minus x squared. Okay, x cube is less than or equal to x squared, so minus x cube is at most x squared. So you are essentially doing an x squared by 2 minus an x squared by 6, which will give you this, right? 1 by 2 minus 1 by 6 is 3 by 6 minus 1 by 6, 2 by 6, 1 by 3, correct. So this is your x plus x squared by 3. But remember, we are not, our f of e is 1 plus epsilon, ln 1 plus epsilon, and there is another minus epsilon here, okay. This minus epsilon takes away this x, and yeah, we finally get the lower bound that we were looking for. F of epsilon is lower bounded by epsilon squared by 3, and hence putting it together we get probability of x greater than 1 plus epsilon. So this is only for the upper tail, okay. X exceeding 1 plus epsilon times mu is bounded by e to the power minus epsilon squared by 3 mu, okay. So here what is the most interesting thing is the e to the power guy, okay. That is what is the highlight of this bound. Epsilon would have been better than epsilon squared, but this is what we get after we do our optimization, okay. Now you should do a similar analysis for the lower tail, okay, but this I am leaving it as an exercise, okay. Try to analyze what happens for probability of x less than 1 minus epsilon mu. Maybe I should also leave a hint here. So here you should again, because the Markov inequality works in the opposite way, you should think of e raised to, doing this as e raised to minus lambda x. Now you see this is a less than or equal to, this is a greater than or equal to e raised to minus lambda 1 minus epsilon mu, but keep your lambda to be positive, okay. Or you could have worked with lambda less than 0, but this is cleaner, okay. Now use Markov's inequality because this is a positive random variable and this is greater than or equal to something, right. So again you multiply and divide by the expectation of e to the power minus lambda x, and then the main job would be computing this expectation of e to the power minus lambda x, okay. So most of these steps you can almost follow, but when it comes to this region of optimizing the f epsilon, it would be slightly different, but actually slightly easier also than this, okay. So yeah, try it out yourself. That's best way to learn. Okay, so now if you combine these two, I'll still prefer to write it as two different bounds, one for the upper tail and one for the lower tail, okay. But remember again this, the required conditions for the bound, your x has to be a sum of n i.i.d. 0, 1 Bernoulli P random variable. So this is a much more restrictive condition than Markov or Chebyshev, right. But yeah, there are certain extensions, you can extend this to sum of i.i.d. random variables with some kind of bound on how much their deviation of the individual guys is. They need not be identical, they need not be indicator guys like 0 and 1, as long as they behave in some nice fashion and they are identical, you have a similar bounds which works in looser and looser scenarios, okay, or more general and general scenarios. But for our purposes, this is the most commonly needed variant, okay. So yeah, and remember there is a small anomaly here. This is what we proved and this is what was left as an exercise. One is epsilon squared by 3, one is epsilon squared by 2. Actually this is better, and by the way this does not even need the epsilon between 0 and 1 assumption, but this is never going to be an issue. Yeah, but actually this by 2 is better. So which means if you want a combined bound for the lower and upper tails, you are forced to use the lower one, okay. The probability that the magnitude of x minus mu exceeds epsilon mu. This is more like very close to the Chebyshev form, but remember that this is a mu here, not an epsilon. Sorry, mu here, not a sigma, okay. Yeah, but now you can add up these two bounds, or to remember it more easily, you can think of it as twice the weaker bound, okay, twice e to the power minus epsilon cube by 3, okay. This is this also, I think, yeah, maybe I should have actually highlighted this portion also. This is also probably the most commonly used version of Chebyshev, okay, the combined bound rather than splitting the upper and lower tail. Okay, so now in the remaining part of this lecture, we would see an application of Chernoff bound. In fact, we will do the work this application with both the Chebyshev bound and the Chernoff bound to see what is the difference. Okay, and this application is from sample surveys, especially this election time. You do a lot of surveys to predict which party would win. Okay, we are taking the most abstracted out or simplistic version of that scenario. Suppose there are n people in a constituency, okay, maybe a parliament constituency or something, and out of that, suppose there are only two parties, okay, one I call the left party and the other I call the right party. I know that some fraction of the people will vote for the left and some will vote for the right. Okay, the fraction which votes for the left, I call it some Pn. So P is a number between 0 and 1. And the remaining will be 1 minus P times n. What is the job? We have to estimate this P. But if you ask everybody, assuming, we will make this assumption that everybody, if asked, gives an honest answer. Okay. There are other models where you assume, at least some people will not be honest when you try to poll them. Okay, and then this is called estimation from noisy data and so on, but we won't get into it. Okay, let's assume that whoever asks gives you an honest opinion, but still there is a cost associated with doing a survey, right? If you have 1 million people in your constituency, you don't want to ask all of them. The question is, can you estimate this P accurately as needed? Usually we go for 1% accuracy or 2% accuracy by asking as few people as possible. Okay, so that's the job. Okay, that's our task. Question is, what is this few? Okay, how many people do we really have to ask to get this accuracy? And the sampling algorithm is also going to be very straightforward. We will pick some k people independently and uniformly at random. Okay. Now, for analysis, I said this is very straightforward. It's very easy to do. But actually, in a real world, picking people uniformly at random is always a question of contention, right? So, for example, if you conduct the survey over email, then it's not picking people uniformly at random. You are biasing towards more educated people who are more comfortable using emails and so on. Even with phone, that's an issue. Okay, if you are the people who do the survey, or if the questionnaire is in English, then again the sampling is biased. Okay, so but again, this is not something that we can get into in a mathematics course, but in a real applied statistics course, picking independently and uniformly at random is really tricky. I think the best way to do it is get the voters list of the constituency. And don't let any human being do it. If a human being does it, there's always a chance of bias. Do this random selection, using a computer by generating random numbers or something, and then that random selection, that list you give it to the people who are doing the survey. Okay, this is very important. Asking your friends is not a random survey. Okay, that's what I really want to emphasize. Okay, many of the time, if you are as a part of a empirical or a field study in a research, this bias is always there. The researcher tends to ask people who was in the known circles of that researcher in 1 or 2 hops. Okay, but that's an aside, it does not really affect what we are going to say. We are assuming that our sampling is independent and uniformly at random, but we are only sampling k people. We are hoping this k would be much smaller than n, but let's see how small. And what is our algorithm or what is our estimate of p? The estimate of p will be denoted as p hat. That's a number of people who said they will vote for left divided by the number of people whom you asked. Okay, so that is the denominator is k. Right, this is a natural thing to do. Okay, now the question is how good an estimate is p hat, right? Now we cannot say something that p hat is accurate enough with 100% confidence, right? Because think about this scenario. Suppose there was only one person who will vote for the left and the remaining n-1 persons would be voting for right. So a good estimate for p would be 0. Right? A good estimate for p would be 0. But there is a very small chance that you turned out to be extremely unlucky and this random sampling actually sampled that lone person k times. Okay, remember, an independent sampling would automatically mean it's a sampling with replacement, right? So there is a very, very small chance. Okay, in fact, the chance is as small as 1 by n to the power k. Okay, but with this chance, you are likely to pick that lone person k times, and then your estimate for p hat would be 1, because every time you asked him, he said he'll vote for the left, so you'll get k by k, which is 1. Okay, so even though this will happen rarely, yeah, at least in rare occasions, the accuracy of p hat can be extremely bad. So we won't be able to give any absolute confidence guarantee on the accuracy of p hat. That's the moral of the story. We cannot be 100% sure that p hat will approximate p. What is feasible is to say something like this: the probability that p hat will deviate from p by too much is at most some delta. Okay, this means with very, suppose this, in general our epsilon and deltas are going to be very small. So we are saying that, okay, with very high probability, that is with probability 1 minus delta, your p and p hat are close enough. What do you mean by close enough? That means their difference is at most some epsilon times p. Okay, again, having this p here is important, especially in scenarios where your p is much, much smaller than half. Okay, otherwise this is difficult to guarantee. Okay, but yeah, so this is usually termed as this probably this is termed as the probably approximately correct kind of statistics. Okay, so it is only approximate and it's only probably correct. Okay, but this is, even though it looks like a kind of very weak statement, this probably here means with very high probability. Okay, and this those who do the FTMSML course also know that your pack learning also derives its name from this kind of a setting. Okay, probably approximately correct. Okay, but now let us analyze what is the k that we require. Our first analysis will be based on Chebyshev. Okay, so let's define these random variables xi to be 1 if the ith sample person says he will vote for left and 0 otherwise, and capital X is the sum of these random variables. Remember, so this is a random variable on which you can apply Chernoff. Okay, because this is a sum of i.i.d, Bernoulli p, 0, 1 random variables. So this is ready for Chernoff, but first let us apply Chebyshev so that Chernoff is a bit glorified when we actually see it. Okay, and what is p cap, by the way? The estimate of p, that is 1 by k of x, right? Because the denominator is also there. This sigma xi is nothing but it counts the number of people who answered left. Okay, so now also notice that your estimate is actually a random variable. Your x is a random variable, so 1 by k times x is also a random variable. So what we report as an estimate for p, there is no randomness in p. P is just the probability of each of those indicator random variables giving 1, or in fact, if you know the entire population, there is no randomness in p if you know how many people will vote for left. Okay, but our estimate is a random variable. Why? Because our estimate is based on random samples. Okay, so it's a function of those random samples, and hence it's a random variable. Okay, now what is the expectation of this estimate? E p hat is 1 by k times expectation of x. Expectation of x by linearity of expectation is k times e of xi, but e of xi is p. So it's k times p, k goes off, you get p. So this is what is known as an unbiased estimate in the statistics context. Okay, at least the expectation of the estimate is the true value. Right? P is the true value, so such estimates are called unbiased estimates. What is the variance of p cap? Again, if you multiply a random variable by some constant, the variance gets multiplied by the square of that constant. Okay, so it's easy to verify. Okay, yeah. So this is 1 by k squared times sigma squared x. But now sigma squared x, I can write it as sigma squared of x1 plus sigma squared of x2, etc. Why? Because you in fact have mutual independence. You only need pairwise independence to write the variance as a sum of variances of the summons, right? So that works. So you have k times sigma x1 squared. Only one k cancels out, right? So one that among this k and k squared, one cancels out, the other will survive. sigma squared x1, we have done this before, is p times 1 minus p. Okay, it's a Bernoulli p, it is p times 1 by p. So this boils down to p times 1 minus p by k. We will take an upper bound of this to be max of p and 1 minus p by k. Okay, because the other actually I could have upper bounded this by the min also, right? And that would have made more sense. Why did I upper bound it by max? Okay, so this is correct, but I could have upper bounded it by min of, this is a better upper bound, by min of p and 1 minus p, because it is like min of that quantity times something less than 1. Okay, yeah, but yeah, then I could have assumed that p is less than or equal to half. Yeah, I think I see the reason. That is because this p appears here, okay? And here if you choose the smaller p, then this is a much more stronger demand, okay? So this would be, in this case, this p would be at least half, okay? So this is at least epsilon by 2. So yeah, that is the reason why we go for the maximum p. This bound could have been improved even with the the smaller p, or with the smaller between p and 1 minus p. Okay, yeah. So but in our context, we will assume more people vote for the left, so p is greater than or equal to half. You could do a similar analysis in the other case also, but yeah, that's anyway not the point here. Yeah, we will go to the Chernoff bound soon. So this is p by k, correct, and which means the standard deviation is at most root of p by k. So what does, now we are ready to apply the Chebyshev inequality. We want to bound this guy, right? P hat minus p magnitude is greater than epsilon p, but this epsilon p, now I have to write it in terms of some constant times the standard deviation. This is how you can write it. Okay, you can see that the k cancels out, the root p and the root p gives a p, the epsilon is already here, and this root p by k is the standard deviation. So the Chernoff bound tells you it is 1 by the square of this constant. So it is at most 1 by epsilon squared pk. Okay, it's 1 by epsilon squared pk. Okay, so and then p is lower bounded by half, which means 1 by p is upper bounded by 2. So I can further upper bound this by 2 by epsilon squared k. Okay, at least I got a very nice looking bound. I think I could have maybe done a bit better if I had chosen 1 minus p there. Yeah, but it is not very clear. Okay, yeah, but anyway, this is approximately, this is the order that you will get. But now what do you want? You want this probability to be at most delta. Okay, so if you want this probability to be at most delta, it is enough that this upper bound is at most delta, right? So you want to pick a k that is large enough so that this guy goes below or equal to delta, right? So you solve for k, you will see that k greater than some 2 by epsilon square delta suffices. Okay, k greater than 2 by epsilon square delta suffices. But this is actually, this epsilon squared and delta in the denominator is costly. For example, even if you want something like epsilon 0.1 and delta 0.1, 0.1 by the way corresponds to 10%. Okay, so this would be like saying 90% accuracy and 90% confidence. Your k is already 2 by 10 to the power minus 1 squared and another 10 to the power minus 1. So 2 by 10 to the power minus 3 or 2000 samples is what you want for this kind of accuracy and confidence. If you want 99% accuracy and 99% confidence, this would be a 10 power minus 2 the square, so 10 power minus 4 and a 10 power minus 2, which would be close to 10 power 6, right? So you need to ask 20 lakh people. Okay, but that is because that's what the Chebyshev analysis will give. let's do the Chernoff analysis for the same thing, right? As we said again, this is ready for Chernoff because you have a sum of Bernoulli, and recall that the two-sided Chernoff tail is this, right? But for this, you can apply this only to x, not to p cap. Okay, so you convert this event p cap minus p greater than or equal to epsilon p in terms of x. So it's essentially you multiplying by k throughout. So this event is same as x deviating from kp by more than epsilon times kp. Remember, kp is nothing but the mu of x, the expectation of x. So this is probability that x deviates it from mu by more than epsilon mu, exactly what the Chernoff bound will tell you. You can directly apply that 2 to the power twice e to the power minus epsilon cube by 3 times mu is kps. Okay, I'll put it back. Now, what we need is that this is at most delta. So in order to guarantee that, we want this upper bound to be at most delta. Now if you solve for k, what you will get is, do this, maybe you can pause and verify. But remember this again, working backwards, because we want a k which is greater than 6 by epsilon squared, ln 2 by delta will satisfy this. Okay? So here the major difference is that earlier we had delta in the denominator, the epsilon squared remains as epsilon squared, but the delta in the denominator become an ln 2 by delta, which is a huge improvement. Okay, so if you see the same numbers, if I substitute, 90% accuracy and confidence needs only 1800 samples. Here you require 2000 samples, not a huge change. But look at the next guy, 99% confidence and accuracy required 20 lakh samples here. Here it reduces, if you do the calculation, to 3,17,900 kind of samples. Typically in all these, election time cephalogist surveys I have seen in the TV channels, they usually use a 2% accuracy and a 99% confidence. Confidence is actually cheap because of the ln 2 by delta that comes in, that's cheaper. But in this case, it boils down to around 80,000 people. Okay. So if you have to trust a sample survey in which there are only two possible outcomes, the order of the number of people you ask should be at least some 50,000. This 80,000 is also an artifact of the analysis. With a tighter Chernoff bound, maybe you could have reduced it a bit. But also notice that n did not figure out in the function for k. Okay, you may have seen that certain statisticians are criticized. They say that all these sample surveys will work in a small country, like Latvia or something, but it won't work in India. In India, you need to ask a lot of people. It's not true. Actually, the number of samples that you have to collect does not depend on the total size of the sample space. That's it only depends on the accuracy and confidence that you want. Okay, so with that we will stop this lecture, and in the next lecture we will keep applying both these. We'll see more applications of Chernoff and Chebyshev bounds. We'll maybe start with Chebyshev bound and focus on how to calculate this variance in slightly difficult scenarios. But that's for the next class. Thank you.